the practical questions in NECO. We have talked about the titration, and we have actually carried out the titration. If you check through our channel, you'll be able to see the practical aspect of the titration. Now we quickly want to, as promised, we want to take some sample questions, possibly the questions that you come across in the NECO practical exam. So that is what we want to talk about today. Before we go into diving into the questions, the sample questions that we have for us, we will quickly take a look at some tips that can help us in the course of the exam. Now, these are some formulas that we'll be using in volumetric analysis. These are some of the formulas that are used in volumetric analysis or quantitative analysis, that's the titration. So we have them here as we have seen. The first one that I have here, I have mass concentration, which is molar concentration times molar mass. We can see that here. That is what we have here. Mass concentration, which is actually what is seen as mass concentration. The formula is molar concentration times molar mass, as that's the formula for mass concentration. So from this very formula, which is the mass concentration formula, we can actually get the molar concentration formula, which is going to be molar concentration time, which is going to be for molar concentration. We have mass concentration divided by molar mass. That is going to be the formula for molar concentration. We'll be having it to be mass concentration divided by molar mass. And then we'll be having concentration. Concentration is going to be moles divided by volume. Moles divided by volume, which can be in dm cube, that's decimeter cube. And number 4, we'll be having CAVA divided by CBVB equals NA over NB. That is concentration of acid over times volume of acid divided by the concentration of base times the volume of base. That equals the number of moles of acid and number of moles of base, or divided by moles of base. So we have CAVA divided by CBVB to give us NA over NB. And then if we have a question that is talking about purity of the substance, this is formula for purity. We have percentage purity here to be in number 5. Percentage purity equals the mass concentration of pure substance divided by the mass concentration of the impure substance multiplied by 100 divided by 1. Again, mass concentration of the pure substance divided by the mass concentration of the impure substance multiplied by 100 over 1. And if it is for the purity, for percentage impurity is going to be 100 minus the percentage purity. If we have calculated the percentage purity, then we can subtract that answer, which is the percentage purity, from 100 to get our percentage impurity. And if you are talking about the solubility of sodium triazocarbonate, which happens to be one of the substances that we'll be dealing with in this particular year. We'll be having, let me put it up here. All right, solubility of the substance now, which is sodium triazocarbonate. We'll be having it to be like this. We have our we have it to be C1V1 equals C2V2. That's the formula that we'll be using. C1V1 equals C2V2, where our C1 possibly the unknown, and we can have our V1 to be the first volume in case we are asked to calculate. We'll be having our V1 to be the first volume. Our C2 is going to be the concentration of the base that has been gotten or that has been calculated. Then V2 is going to be the second volume, probably, that has been given in the question. And then if we are asked to calculate the dilution principle formula, we'll also be using C1V1 equals C2V2. That is what we're talking about here, that's solubility. And then number 9 is mass of the salt formed. If we are asked to calculate the mass of the salt formed, for example, we'll be having concentration of base times volume that is given in dm cube, not the one in the volume of base, not the volume of pipette used, not 25 centimeter cube for this particular one. That is the volume of base in concentration. And then we have it multiplied by molar mass of the salt that is formed. And then we have the 10th one to be volume of gas at STP. Volume of gas at STP, we'll be having the concentration of base times the coefficient of the carbon dioxide. That is, if you are asked to calculate the volume of gas, like the gas that is given up in this particular reaction is going to be carbon dioxide. So if you are asked to calculate the volume of gas at STP, we'll be having it to be concentration of base times the coefficient of the gas formed times the volume given in dm cube times the molar volume of the gas, which is going to be 22.4 dm cube. So these are some of the 10 formulas that has been given here. There are some of the likely formulas that will be used in solving some questions that you probably can come across. So I indulge all of us to try as much as possible to be attentive and pay attention to what we'll be talking about. Now here I have indicators. Now in the practical question, you'll be having the number one question to be quantitative analysis, that's volumetric analysis or titration, and then number two is going to talk about salt analysis, which is the qualitative analysis. We're talking about the quality or the properties of the salt that is going to be given. And then number three question is going to be random questions. It is also practical questions, but it will come in form of theory. So they could ask different types of questions. So these are examples of indicators that are used in volumetric analysis. Okay, so I just decided to put this here to help to help broaden our knowledge on the possible questions that we can come across and what the answers will be when we come across such questions. So we have certain indicators that are used to mark to identify certain substances if they are either acidic or basic, or even if they are neutral. So how do we now identify these substances and their changes in the indicators and their changes in the substances? So we have a few of them that I have listed here, like I have listed methyl orange, phenolphthalein, bromothymol blue. These are common indicators that are used. We also have some other indicators, like we have the normal paper indicator, which is the litmus paper. It is also an indicator. We have the universal indicator. Those are other types of indicators. But for the purpose of practicals, we majorly use the methyl orange, the phenolphthalein, and once in a while we can use bromothymol blue, or we can even use glucose as our indicator. So now, what is the reaction that is formed when we use methyl orange in acid? The resultant coloration, the change in color that is given, is going to be pink. When we make use of orange and methyl orange, when you drop methyl orange in as an indicator into an acid, what you get is a pink color. But when methyl orange is dropped in a base, what you get is yellow. And when methyl orange is dropped in a neutral substance or an at point, what you have is going to be orange. So when you are using methyl orange as an indicator, you have dropped it in your base and that's giving you yellow color. The end point of the reaction, where you notice the end point of the reaction, that is when the acid mixes with the base to form a neutral substance, you notice that there is going to be a pink color change. So that is about methyl orange. For phenolphthalein in acid is colorless. In base, phenolphthalein gives a pink coloration, and at neutral or end point, it gives also a colorless solution. So you need to be careful how to identify from to differentiate between the acid and the end point or the neutral substance of the phenolphthalein. And then we have the third one there, which happens to be the bromothymol blue, which I have listed here. Bromothymol blue is the third one here. So for bromothymol blue, we have it to be in acid, it gives a yellow color. Bromothymol blue in acid gives yellow color. In base, it gives a blue color. And then in neutral or at end point of the reaction, it gives a green color. So these are some properties of indicators that you probably can come across. Now, this is the third one that we have here. I'm talking about suitable indicators for titrations. Now, indicators are chosen based on the type of reaction you want to carry out. The type of titration you want to carry out will inform or will direct you on the type or on the choice of indicator that you are to use. So if you have a strong acid and a strong base, for example, you have a strong acid to react with a strong base, any type of indicator should do that for you. Using any type of indicator, you'll be able to carry out the reaction between a strong acid and a strong base. But if the reaction is between a strong acid and a weak base, you'll be needing methyl orange as an indicator. The most suitable indicator for a strong acid weak base titration is methyl orange. And if the reaction is between a weak acid and a strong base, if you are carrying out a reaction between a weak acid and a strong base, the best indicator for that type of reaction is the phenolphthalein. The phenolphthalein is most suitable for a weak acid strong base titration. And lastly, if you have a weak acid and a weak base, no suitable indicator is used. Any type of indicator you use probably will not even be giving you a suitable result. So because the reaction is going to be very vulnerable. So for weak acid, weak base, we have no suitable indicator. So all of these that have been listed are the possible if it comes your way. These are answers to some practical questions that can come in your number 3 in form of the practical question. So having taken this now, let us quickly take a couple of questions that we will use to help ourselves, familiarize ourselves with what practical questions, particularly in quantitative or volumetric analysis, is about. So that will bring us to talk about these questions here. So the first question I have for us, question 1 there, it says A is a solution containing 0.0396 moles. Again, A is a solution containing 0.0396 mole per dm cube of H2SO4, and B is a solution containing 3.6 grams per dm cube of X2CO3 salt. Now, A, put A into the burette and titrate with 25 cm cube or 20 cm cube of B using methyl orange as an indicator. Tabulate your burette reading and calculate the average volume of acid used. B, from the results and the information provided above, calculate 1. The concentration of B, that is the base, in moles per dm cube. 2. The molar mass of B. 3. The value of X in X2CO3. Now, for this question, we are going to assume our average tetra value to be 21.3 centimeter cube. We are going to assume our average tetra value to be 21.3 centimeter cube. So, let us now go into solving that. Now, before we do that, let's quickly take some basic informations. Now, we could be asked at any time to calculate the molar mass of the substance. The substances that we have in sample A. Our sample A, which is the acid. Our sample A, which is the acid. We have it to be the H2SO4. So if we are asked to calculate the molar mass, the molar mass of, before we go to the molar mass, let's see the mass. If you are asked to calculate the molar mass, let's just go with molar mass once and for all. The molar mass of A, which is the H2SO4. Now we have H to be 1, C, because we will get to that, C also is 12, we have S to be 32, O to be 16. So this is how to calculate the molar mass. We have H2SO4 now, so we'll be having it to be, our H is 1, so we have 1 times 2 plus S, which is 32, plus our O is 16, but our O is in 4 places. So this is what we have. Sorry, let me clear this very well. We have this here. So 16 times 4. So we have 2 plus 32 plus 16 times 4, which is going to give us let's see 16 times 4. 16 times 4 will be having 16 times 4 will be having 64. So we have 64. So all of it is going to give us 60. We have 64 plus 32 plus 38 is going to give us 98 grams. So that is the molar mass for H2SO4. And then for our sample B, which is our base is sodium triazocarbonate. So the molar mass of our B, which is the sodium triazocarbonate, we'll have it to look like this. Our sodium is 23. Let me put that here also. Sodium is 23 in 2 places, plus our carbon, which is 12, plus our oxygen in 3 places. So 23 times 2 is going to give us 46 plus 12 plus 16 times 3 now. 16 times 3 16 times 3 is going to give us, we'll be having it to be 48. 16 times 3 is going to give us 48. So we now have 46 plus 12 plus 48, which is going to give us 106. We're having 106 grams. So that is the molar mass of our salt B. So of our base, of our sample B, which is the base, as sodium triazocarbonate. So you could be asked to give the reaction, the equation for the reaction. So this is what the equation for the reaction is going to be. The equation for the reaction is going to look like this. We'll be having it to be, since it is a reaction between H2SO4 and sodium triazocarbonate, we'll be having it to look like this. H2SO4 plus sodium triazocarbonate. So we'll be having it, since it's acid and base, it is a neutralization reaction, so we'll be having this. We'll be having this sodium tetraosulfate plus carbon dioxide and water is going to be given off. So we have it in ratio 1:1. Yes, that is in ratio 1. Our acid to our base is in ratio 1:1. So these are some informations that you'll be needing in the questions that we have to solve from this moment onward. So let us kick it off now by taking the first question. So the first question again says we should calculate the concentration of B in moles per dm cube. Let me quickly take the question again. A is a solution containing 0.0396 moles per dm cube of H2SO4. B is a solution containing 3.6 grams per dm cube of X2CO3 salt. A. Put A into the burette and titrate with 25 cm cube of B using methyl orange as an indicator, and tabulate your reading and calculate the average titral value of the acid used. Then B, from the results and information provided above, calculate 1. The concentration of B in moles per dm cube, 2. The molar mass of B, and 3. The value of X in X2CO3. Now we are going to assume that our average titral value is going to be 21.30 centimeter cube. Always make sure that your titral value is in 2 decimal places. That is very, very important. Now let us go to the first answering the first question, the molar concentration of B. So we have here, let's move to the next page. 1. Question 1. The molar concentration from the reaction that has been given molar concentration of A equals 0.0396 moles per dm cube. Moles per dm cube, that is the value that has been given from the question. And then we have the mass concentration of B. The mass concentration of B to equal 3.6 grams per dm cube. It is very, very important that you are careful of the formulas and their units. Now, to calculate the concentration of concentration of B in moles per dm cube, this is the formula that we'll be using. We'll be using this formula, CAVA over CBVB equals NA over NB. That is the formula that we will be using. Now, let us quickly cross multiply. So if we cross multiply, this is what we'll be having. We'll be having CAVA NB equals CBVB NA. So since what we are looking for is the concentration of B, so our CB equals, we have CAVA NB all divided by, all of that is going to be divided by, we have it divided by the VBNA. So that is what we'll be having. So let us see what that is going to be. We have it to be, from our question, we have 0 as our CA. We have 0. Okay, let me put it down here. We have, from our question, we have 0.0396 times, we have our value there to be, we are assuming our tetra value to be 21.30. So 21.30, 0.0396, okay, 21.30. Then our NB here is 1, all divided by, we have all of that divided by, we have our VB, that is the volume of our pipettes, which is 25 times 1. So what we'll be having, the resultant that we are having now, 0.0396 times 21.30 times 1 is giving us 0.8, 4348, all divided by 25, divided by 25 is giving us, divided by 25 is giving us 0.00337,392. So if you take these to three significant figures, always leave your answer in three significant figures. We'll be having it to become 0.0337. And since it is concentration that you are looking for, it's going to be moles per dm cube. So that is going to be our final answer for this. So this is our CB. Our CB is 0.0337 moles per dm cube. That is our CB. So now we are going to use that to calculate other values, other questions in. We're going to use it to calculate other things in the question now. So let's take the next question now. The next question we have for number 2. Our next question is this. Sorry. Number 2 now. we have the next question. The next question for number 2, it asked us to, it said the molar mass of B. We're calculating the molar mass of B. That is what we want to calculate now. So let us quickly do that. The molar mass of B. Molar mass of B. So we're using this formula, mass concentration. Mass concentration equals molar concentration times molar mass. Molar concentration times molar mass. So since it is molar mass that we are looking for, molar mass equals the mass concentration divided by, we have the mass concentration divided by the molar concentration. Mass concentration divided by molar concentration. So that is this. We have our molar mass. Now, our molar mass equals 3.6, which was given in the question as the molar concentration of B, divided by, we have it divided by the molar concentration that has just been calculated, which is 0.0337. So when we do that calculation, we will have it to equal, we will have it to be 106.824925. So to 3 significant figures now, we will have it to equal 1.06 grams per mole. 1.06 grams per mole. That is going to be the molar mass of our B. Molar mass of B. So that is it. And now the next question there says we should calculate the value of X in X2CO3. Value of X. Value of X in X2CO3. So this is the formula that we'll be using. X2CO3 equals the molar mass. And we have just calculated the molar mass now to be 106. We have just calculated the molar mass now to be 106 grams per mole. So we have our X2. We have it to be 2x plus 12, which is the mass of carbon, plus our oxygen. Our oxygen is 16. We have our oxygen to be 16 times, for this value now, we have it times 3. So that is going to give us 106. So all of this now, we have it to be 2x plus 60 to give us 106. So 2x equals 106 minus 60, and that is going to give us, we have it to be, okay, let me move to the next page so we don't model everything, or let me just roll a line here to complete that. Okay, alright, so if we have our 2x equals 106 minus 60, now we'll be having that value there to look like this. 2x equals, we have it to be 2x equals 46. 2x equals 46. So our x equals 46 divided by 2, and that is going to give us 23. So the value of our x in the CO3 is, the value of our x in X2CO3 is 23. So that is the answer for the questions that we have for the first question. So let us see what the next question is talking about. The next question now says we should look at question 2 here. Says A is a solution of tetraoxosulfate 6 acid. B contains 1.8 grams of sodium triazocarbonate. A is a solution of tetraoxosulfate 6 acid. B contains 1.8 grams of sodium triazocarbonate in 500 centimeter cube solution. A. Put A into burette and titrate with 25 centimeter cube of B using methyl orange as an indicator. Then tabulate your reading. So the questions we have there: 1. Calculate the concentration of B in moles per dm cube. 2. The concentration of A in moles per dm cube. 3. Concentration of A in grams per dm cube. So we are assuming, for this particular question, we are assuming our average tetra value to be 21.40. That is what we'll be using for the average tetra value of this particular question, 21.40 centimeter cube. So let us go to answering that. So question 2 now. Question 2. That is what we want to answer now. So the first thing we need to know from the question, we have mass concentration of B. Let us quickly calculate the mass concentration of B, so it will be easier for us to calculate the concentration of B in moles per dm cube. So the mass concentration of B in grams per dm cube equals, we have it to be grams divided by centimeter cube times 1000. So this is what we'll be having. We have it to look like this. We are given 1.8, then divided by 500, because that was the thing when I was given in the question. So divided by 1000 over 1. So we'll be having it to be 3.6. So to 3 significant figures now, to make it easier, to 3SF, we'll be having it to equal 3.60 grams per dm cube. So this is what we will use in our calculation now. So to calculate the concentration of B in moles per dm cube now, we have this formula to be used. Mass concentration, that is the reason why we had to calculate mass concentration earlier on, because it wasn't given in the question. So mass concentration equals the molar concentration times the molar mass. Molar concentration times the molar mass. So that gives us the molar concentration to look like this. Molar concentration equals mass concentration divided by the molar mass. So that is, we are having it to look like this. Our CB, which is concentration of B, equals, from the question, from what we just calculated here, our mass concentration is 3.60 divided by our molar mass. The molar mass for sodium triazocarbonate is 106 grams per gram. So equals, so 3.60 divided by 106 is going to give us 0.033962. So to 3 significant figures now, to 3SF, we're going to be having it to become 0.0340 moles per dm cube. So that is going to be our CB, our concentration of B in moles per, our concentration of B in moles. That's our molar concentration for B. So the next question says we should calculate the concentration of A in moles per dm cube. Concentration of A in moles per dm cube. So this is how we're going to do that. We're going to be using this formula, CA. The formula we'll be using is CAVA over CBVB equals NA over NB. That is the formula we will be using. CAVA, sorry, okay, CAVA over CBVB equals NA over NB. That's the formula we will be using. So we have that. Let's quickly cross multiply. When we cross multiply, we'll be having it to look like this: CAVANB equals CBVBNA. So since we are looking for A, CA equals CBVBNA, yes, divided by, we have VANB. So from here we know we have accepted that our concentration of B is what we have calculated earlier on. So we have it to be 0.0340. We have 0.0340 times 25, which is the volume of our pipettes, that's the volume of the base, times 1, that's the number of the ratio of the reaction now. Given us the number of moles of acid. So all divided by, we have it divided by the volume of acid that is used. So here we have accepted that the volume of acid that is used is 21.40. 21.40 times 1. So what we'll be having here is going to be, we'll be having 0.85. When we multiply 0.0340 times 25 times 1, we'll be having 0.85 divided by 21.4. Divided by 21.4. So that is going to give us this. We'll be having it to be 0.0397196. So to three significant figures now. To three significant figures, it is advisable you leave your answer in that. It gives us 0.0397 moles per dm cube. So that is the concentration of our A. That's going to be the concentration of our A. Concentration of A in moles per dm cube. So the third question there says we should calculate the concentration of A in grams per dm cube. That is what the third question there is saying. Like we can see here, calculate the concentration of A in grams per dm cube. So this is how we are going to do that. Number three, we have concentration of A. Concentration of A. Concentration of A in grams per dm cube. So we use this formula: mass concentration equals molar concentration times molar mass. That is what we are going to be using for that. So we have it to look like this: 0.0397, sorry, this is supposed to be 397, 0.0397 times 98, which is the molar mass of our acid H2SO4. So we'll be having that value to be 3.8. That's when we multiply 0.0397 times 98. We'll be having it to be 3.8906. 3.8906 to three significant figures now, to 3SF. We will have it to equal 3.89 grams per dm cube. So this is going to be the value of our concentration of A in grams per dm cube. So that is what the second question is looking like. So let us go to the third question now. The third question says calculate, A is a solution containing 0.0396 moles per dm cube tetrazosulfate 6 acid, while B is a solution of impure sodium triazocarbonate containing 5.2 grams dm cube of solution. Now put A into a burette and titrate 25 with 25 centimeter cube using methyl orange as indicator. Tabulate your reading. So you are now asked to calculate the concentration of B in moles per dm cube, concentration of B in grams per dm cube, the percentage purity of sodium triazocarbonate, then the percentage impurity of sodium triazocarbonate. So for this particular question, we are assuming our A, we are assuming our average tetra value to be 21.45 centimeter cube. We are using 21.45 centimeter cube. That is what we are using for this particular question. So let us go to answering that question 3 now. Question 3. So from the question now, we have some informations like telling us that the A is containing 0. So that's the molar concentration of A, 0.0396 moles, and then we have the mass concentration of B to be 5.2 grams. So that is what we want to use to solve the question that we have before us now. So the molar concentration of A, equals 0.3, sorry, 0. Let's check the question very well. 0.0396, okay, 0.0396 moles per dm cube. And then we have the mass concentration of the impure sodium triazocarbonate. Mass conc of impure B equals 5.2 grams per dm cube. So let us now calculate the concentration of B in moles per dm cube. Concentration of B in moles per dm cube. Concentration of B in moles per dm cube. So we are using this formula. We are using CAVA over CBVB equals NA over NB. So as usual, we cross multiply. So we'll be having CAVA NB equals CBVB NA. So we are looking for the concentration of B. So we have CB equals CAVANB divided by VBNA divided by VBNA. That is what we'll be having. So that is going to give us this. We'll be having it to look like this. Our CA, the molar concentration for our A is 0.0396 times 21.40 times, 21.45 times 1, all divided by, we have it all divided by 25 times 1. 25 is the volume of our base. That's the volume of the pipette that is used. So we'll be having it to look like this: 0.84942 divided by 25, which is going to give us 0.0339768. So to 3SF now, to 3 significant figures, we are having it to become 0.0340 moles per dm cube. So that is the volume of that's the concentration of our B in moles per dm cube. So the next question is asking us to calculate the concentration of B in grams per dm cube. Concentration of B in grams per dm cube. So this is the formula that we'll be using. We'll be using this formula: mass concentration equals molar concentration times molar mass. So what we'll be having now, we'll be having our mass concentration to equal 0.0340, we've calculated that earlier on, times our molar mass for the sodium triisocarbonate, which is 106, and that is going to give us, we have 3.604, and then to 3SF, the 3 significant figure, is going to give us 3.60 grams per dm cube. So that is our concentration of B in grams per, the mass concentration of B. The mass concentration, mass concentration of B in grams per dm cube. Let me put this so we don't get confused. Mass conc B in grams per dm cube. So we now have the next question talking about the percentage purity. Okay, let me put that in our next page here. That's number 3 now. Percentage purity. Percentage purity of B. So from the formula, we are going to be using this percentage purity equals, we have the mass concentration of pure substance, the mass concentration of pure sodium triisocarbonate, divided by the mass concentration of impure sodium triisocarbonate multiplied by 100/1. So that is the formula that we will be using. So that is going to give us this. We'll be having 3.60, which is the mass concentration of the substance, divided by the 5.2 that was given in the question as the mass of the impure substance, multiplied by 100/1. So when we have that and we do the calculation, what we'll be having is going to give us 69.23. Sorry, let me correct this. 69.230769. So to 3 significant figures now, to 3SF, we'll have it to look like this. It's going to become 69.2%. That is the percentage purity. Percentage purity is 29.2%. So the fourth one now is asking us for percentage impurity. Percentage impurity of B. Now we're going to be having is the formula that we'll be using for percentage impurity. Percentage impurity equals 100 minus the percentage of purity. So since we have just calculated the percentage of purity, so we'll be having 100 minus 69.2. So that is going to give us 30.8%. So this is going to be our percentage impurity. The percentage impurity in the sodium triisocarbonate. So this is how we solve the question of percentage impurity. So let us go to the next question now. The next question that we have in this session. So the next question that we have here is talking about A, a solution of dibasic acid H2X, and then B is a solution containing 0.034 moles per dm cube of sodium triisocarbonate. So we are asked to put A into the burette and titrate 25 centimeter cube of the base against the acid, titrate the acid against the base using methyl orange as an indicator. So the equation for the reaction that is given, we have H2X plus sodium triisocarbonate to give us Na2X plus carbon dioxide and water. So from this reaction now, we are asked to calculate the concentration of A in moles per dm cube, the molar mass of A, given that the solution A contains 3.9 grams per dm cube of acid, and then we also asked to calculate the value of X in H2X. So those are the things that we are asked to calculate. So let us move to the next question now. That's question 4. Question 4. So question 4 is what we want to handle now. So we are having, for this particular question, from the question we are going to be using 21.60 as our average tetra value. So let us see. The molar concentration of B that was given in the question, molar concentration of B equals 0.0340 moles per dm cube. We can see that right here, 0.034 moles. That is what we have here. You can see it's a 0.034. That's the molar concentration for the B. So going back to our table now. So to calculate the concentration of A in moles per dm cube, that's the first thing we're asked to calculate. Concentration of A in moles per dm cube. So let's use this formula. We'll be using CAVA over CBVB equals NA over NB. Please, it is very, very important that you get yourselves acquainted with the formulas. It is very, very important. Please, for anything you're doing, you need to master these formulas. All right, so let's cross multiply as usual. When we cross multiply, what we'll be having is going to be CAVA. I'm doing this continuously so as to get us acquainted with the process. So we have CAVA NB equals CBVB NA. So we are calculating for CA. So CA equals CBVB NA divided by VA NB. And so what we'll be using for that, we'll be having our CB from what we have been given here, 0.0340 times our VB, which is going to be 25 centimeter cube, times our NA, which is 1, all divided by, we're having all of these divided by the volume of acid, which is 21.60 times 1, 21.60 times 1. And so when we do the calculation, what we will be having is going to be, we'll be having this as our value, 0.85 divided by 21.60. So when we do this calculation, 0.85 divided by 21.60 is going to give us 0.0393585. So when you do this and you have it to three significant figures, you'll be having it to equal 0.0394. 0.0394 moles per dm cube. So that is the value of our CA. Our CA is 0.0394 moles per dm cube. So let's go to the next question now. The next question is asking us to calculate the molar mass of A. Molar mass of A. So how do we calculate the molar mass? Let's use this formula. The mass concentration equals molar concentration times molar mass. So when we are using this formula, we are looking for the molar mass, isn't it? So what we'll be having is going to be molar mass equals mass concentration divided by the molar concentration. So we are having it to look like this: 3.9 divided by 0.0394. 3.9 divided by 0.0394, and that is going to give us 98.984772. So when we convert it to three significant figures, we'll be having it to be 98.9. So 98.9 grams per mole. So that is going to be the value of our molar mass of A. And then the last question there is asking us to calculate the value of X in H2X. The value of X in H2X. So this is what we use. H2X equals the molar mass. We want to know the value of the X in the H2S. So the value is, this is what we are going to use. We have our H to be 1. The mass of H is 1. Mass of hydrogen is 1. So we have 1 times 2, because 1 is in two places. 1 times 2 plus X. 1 times 2 plus X to give us the molar mass of A, the molar mass of our H2SO4 to be 98.9 from the question we just calculated in B. From this particular one, we have our B, our molar mass of A to be 98.9. So that is what we are using here. So 1 times 2 plus X equals 98. Okay, let me put our X like this so we don't get confused. Let me write our X like this, just for this particular session. Let me put our X like this, so it doesn't look like time, so we don't get confused. So 1 times 2 plus X gives us 98.9. So we'll now be having 2 plus X equals 98.9, and then X equals 98.9 divided, 98.9 minus 2, because it is not 2x, it is 2 plus x. So 98.9 minus 2, so our X equals 96.9. So that is the value of the X that we have in the H2SO4. So that is how the fourth question is being treated.